carry on from where we stopped last week. Last week we were trying to look at the introductory aspect of the course and tried to have basic definitions and try to appreciate where simulation and modeling is applicable. And we discussed a number of aspects to do with simulation. So today, I want us to look at modeling. Because last time we talked about simulation, so we want to talk about modeling. After understanding modeling, then now we have fully understood the concept of rather the course. So I'll share my screen so that then we can start. So hopefully everybody is able to see. And because of the streaming aspect and the management of credit, I will remove the video from my side. But if you are fine, if you experience challenges, you can always tell me so that I can actually minimize what you are able to see from the side. So what is it that you want to do today? It's always important to be able to appreciate the objective that we want to achieve today. And how does it fit into the bigger picture? So as a learner, you should always try to see whatever we are doing in the broader picture of what we are calling the learning objective. That whatever that you want to discover today or to learn today, how does it then assist you achieve this objective? Because that is the essence. When we say the learning objective is, we are trying to answer the question of the relevance of this unit in your academic pursuit. So by the end of the lecture, we have broken this lecture into two. There will be this and then there will be others. So there'll be lecture 1, that's first hour, lecture 2, second hour, lecture 3, third hour. So by the end of the lecture, the learner should be able to explain what is system modeling. In other words, be able to explain what it is. We'll also try to understand what are the elements and events in a system modeling and what role do they play. We'll also then explain the uses of models and be able to look at the characteristics of our system state variables. And the most important is not only looking at these characteristics, but see those characteristics into a model. And we'll try to classify system models. We classify, and then later on we'll be looking at those models that we have classified. So the first thing, therefore, we want us to look at is what is a system model. And before we look at a system model, we just want to say, what's a model? Most of us will want to ask ourselves, have I ever used a model? Because that's the most critical thing. So that then you can relate what you know to what you don't know. I want to take you very far, a bit far. Just reflect on your academic pursuit when you were little pupil somewhere. You did a model. Perhaps you were using I'm sure say Cray. There are those who are from the Philips, they understand it. Those who are the upper nights, town dwellers may not be very familiar with the Cray. With them, they'll be talking about this, not the name you call it. So I'm going to ask who's going to tell us? Maybe Newton. How do you call it? The one that you bought and you used to model something. What's the name given to that? Then, Newton, we can't hear you.
The one you
Yes,
buy.
yes.
I didn't buy. I'm from
Oh,
the
you
village.
are
I didn't
from
buy
you
one.
are you are like me. So good. So we are connected. Who can tell us then? Maybe who can tell us? Somebody has given an answer on the chat. Yes, great. Stacy Omwando has said Solomon Kipto has said public for everyone to see. Great. That is it. So if you see on the chat, that is it. Plasticine, right? So whether you use plasticine, you use clay, whatever thing that you use, whatever you were coming up with, we call it a model. You were coming, sometimes you could make maybe a car, or you could make anything. That is a model at it is very basic level. Later on, you moved up and started actually doing other things for others could, yeah, sure. There's a question on the chat. Is it okay if you can turn your camera off? Yeah, so thanks. Yes, it is okay. That's what I was asking. If it's affects, then I put it off. Correct. I put it off. So so later on, there are those who started now making models using wires, using papers. You could, so that's what we call a model. So the only thing that we are changing, other than the use of plasticine or clay, the way you were modeling, now we want to actually change and actually say, can we draw that in a diagram that's pictorial form? Now, after presenting in pictorial form, can you convert that which is in pictorial into mathematical form? Now, if you reflect on that, then you can actually go back into your first foundational courses that you did when you joined university. There is the first unit that you did on introduction to programming. We talked about an algorithm. And then you could actually present it using maybe a diagram. And then this diagram, you could call them flowcharts, right? So a flowchart is a pictorial representation of an actual system, whereby you are saying in a flowchart, you know, there is what we call the input section, and then there is what we call the processing section, and then there's the output section, meaning that all those components of an algorithm which is in the form of a flowchart can be changed and be presented in a manner that you can group them. So this is the input section, this is the processing section, and then the other section which becomes what you call the output section. You went on, and then when you are doing data structures and algorithm, you said that to find an algorithm can be presented using mathematical form. And some of those algorithms, then you started saying categories of algorithms. Those becomes also what we call mathematical form of representation of a system. So we can therefore say that a model is a representation of an actual system, either in a pictorial form or a mathematical form. But now, for this particular case, what are we expected to do? We are supposed to know both, to represent something in pictorial and also to represent something in mathematical form. More importantly is the mathematical form. The reason being the mathematical form gives us the logical aspect of a model. You can say therefore, it is therefore an abstraction of a real system. The word abstraction you can now relate to the concepts of object-oriented programming that you've done. Abstraction is one of the concepts of object-oriented programming. And abstraction, as they were, is a representation. Abstraction is a representation. I want to ask a question there so that then we are able to relate this. Who can give an example of abstraction in object representation? How do we achieve abstraction in object representation? Any one of us can raise their hand and then be able to tell us an example of abstraction in object-oriented programming. Or how do we achieve abstraction in object-oriented programming? All right, perhaps as you reflect, yes, Anton.
Object-oriented programming is when you define a function in a class. Yeah, when you define a function in a class, when you actually get to call it, you can just you can just give it the name of the function. Then, and instead of writing the whole code on how the function does it, you just call the function and maybe give it an argument, and the function will run. So you don't need to write the whole how the function does it. You just need to call the function. So it abstracts. It hides the details on how the function is actually doing it, actually being performed.
Actually, how we achieve abstraction. So we use a class, and within our class, we define a function. Which function we call it anywhere within our class or outside, and then so that element of hiding the internal implementation of a function is abstraction. Thank you, Kafai. So you can see ideally abstraction is a way of representing therefore a model. So we can therefore from that definition get to appreciate that you have interacted with modeling. Okay. Another section where you've done modeling is in database, which I suppose you've done a number of database units. When you are designing a database, the first point is what we call, the logical model. So where you are able to identify and represent an entity. And you represent this entity sometimes into what we call an entity relationship diagram. So in that case, inside the way you are going to implement it is not necessarily defined within that entity. So thank you. So that is what a model is. So number two, model, we have said, is that abstraction of real system or a representation of a real system either in pictorial or mathematical form. The next thing is, how then do we achieve this abstraction? How do we come up with abstraction? We do this by the use of technique which we call now modeling. So all concepts that you reuse procedures that you use in order to come up with the model is what we call modeling. Therefore, we say modeling is the application of methods. It may not be methods. I should have added another word, the techniques. So, like now, when you coming up with an ERD, you use specific techniques and procedures so that then you come up with what? That representation. So modeling is the application of methods or mathematical methods to analyze complex real-world problems in order to make prediction. So methods to analyze complex real-world problems in order to make prediction about what might happen in various actions. You might not only make predictions. As I've said, like when you model a database, you are not going to make prediction, you are going to store, right? So, but the only thing here is you are representing a real world. So that's why we say an entity. An entity is that which we can store data on, what we can relate with, what has, attributes we can describe about it. And therefore, modeling, in simple terms, is the process of coming up with a model by the application of methods. These methods, specifically, let us now, for purpose of this course, say mathematical methods to analyze a situation and then come up with a representation. And the whole thing here is you want to solve the problem. So, and therefore, to be able to do modeling, there are fundamental things that one needs to know. Fundamental things that one wants to know, which we call now system model elements and the events. So elements are not the same as events. So we want to look at what are therefore. Essentially, we call them components of a model. Now, to be able to see this, I want us to apply ourselves into the thinking of a class. We say the components of a class. And when I say a class, please take your mind into object-oriented programming. What's a class? We know a class could have, a name, could have data members, could have functions, and such kind of things. So therefore, a model, we want also to say, what does a model have? So a model will have what we call an object. A model can have an object. Now, an object is an entity in the world. Because you say model a real problem. A real problem, meaning must have entities. So that's why we call an object is an entity in the real world. For instance, if we are modeling a disease, right? So in this particular case, a disease, the name of that disease become an object. Why should it become an object? Is because we can identify characteristics that it has. We can identify, we can relate it to the various characteristics that it has. So essentially, I think that a class, that a model must have this that we are calling an object, and an object we can actually be able to identify its attributes. I need to link where we come from here. You say a model is a representation of an actual system. And we are saying it can be either in pictorial or mathematical form. And hence, one can actually say it's abstraction of a real system. Then to be able to do this, we are saying we need to carry out modeling, which we are saying is the process of coming up with the model. And for us to be able to do this, we are saying we will need to apply mathematical methods to analyze that problem. Now, how then do I need to analyze this problem? I need to identify the elements of that problem. The elements of that problem. If I'm able to analyze the elements of that problem, then I can actually relate it to a real environment. And so we are saying one of the elements is an object, and an object we are saying is an entity. What do we know about entity from our programming or database aspects? So I will want to invite any one of us to tell us a little bit more about aspects of an entity. So aspects of an entity, and in answering this, please reflect. Any one of us, please raise your hand, then you be able to explain a little bit more on what's an entity. Any one of us, please raise your arm and then be able to contribute. Yes, Moses?
An entity is anything that can basically contain data. For example, a car can contain data on the engine, the color, that stuff.
Great, thank you. Anything that can contain data, meaning we can store data about it. Thank you, Moses. And he has given a good example, a car. We can talk about the engine of the car, isn't it? We can talk about the color of the car. We can talk about the size of the car, the model of the car. So anything that we can store data on, that's an entity. We normally say, again, is that of business interest, right? Something that we need to store data on. Thank you, Moses, once more. And therefore, an entity, you can see it relates to an object. And therefore, modeling to take place, we must actually identify the object. I want us to reflect on disease like the COVID-19, which is really a stress, and I believe because mass it will go. What are we looking at? We can talk about the characteristics of COVID. So COVID is an object. We can store data on aspects to do with COVID and such. Such an object can exhibit varying behavior depending on the context in which it is studied, as well as the aspects of its behavior which are under study. What does that mean? If we look at the example Moses has given us, Moses Karanja, he's talked about the engine of a car. So the engine of a car is not the same for all cars. So meaning, therefore, if I'm looking at different cars, then the engine is going to vary. And that's what we say, an object can exhibit varying behavior. Why is that example important? Because we know an object, when manipulated depending on the changes of the attributes it has, it becomes something slightly different. So when we look at, therefore, varying behavior, I want us, therefore, now to apply ourselves into the science which you are very good at. That behavior is a method. It determines how that object is going to be. So if you have a top, let's say, a tractor, so the engine is in such a manner that it's going to be used for, that aspect. So meaning, therefore, the behavior is dependent on aspects to do with attributes of that object. The next thing that we need to know, which is an element of a model, is what we call base model. A base model, we normally call it hypothetical or an abstract representation of the object properties. Now, so that hypothetical or abstract representation of the object's properties, its behavior, which is varied in all possible contexts and describes all the object's facets. That looks quite complex, but I want to make it easier. And I will use your programming, more important, the C++, which I think you have done. We talk about an abstract class. There are different forms of classes that we can have in a system. One of it is what we call abstract class. I want to invite any one of you to explain what's an abstract class. Then I will then relate that abstract class into what we are calling a base model. Any one of us to tell us what's an abstract class, or the characteristics of an abstract class from your programming classes. Yes, Waweru.
An abstract class is basically like it has methods and attributes. However, those methods and attributes have no implementation. So the attributes have no values and the methods have no implementation. So it's just used as a reference to make other classes.
Thank you. Well put. Thank you, Mathenge. That is what we call an abstract class. That we can also therefore look at an abstract as a template, which you can therefore use to build anything that you need. We normally say the implementation of that class is elsewhere. Okay. Now, we normally say that an abstract is that, for instance, which you realize that all those things that are likely to be needed in many classes, they'll better put in an abstract class, because then we can call them instead of keeping on dividing them sequentially. That is a base model. If you understand the concept of abstract class, an abstract class is the same as a base model. No, but I want to also come to a general understanding. I think you, for those of us who come again from the rural side, but I think also in the urban setup, you've seen the shoe cobblers, the people who mend shoes in the streets. They usually have a frame, an architectural frame of the feet that they use to design or to come up with with the shoe that they want. So that frame, that structure of the feet of a human being is a base model. If you look at that base model, therefore, it is hypothetical. Hypothetical means it's conceptual. It's something that they think it is going to be like this. That the feet of a human it will be like this, and therefore the shoe I'm going to come up with is going to be like this. The same base models are used extensively. For those of you who have a chance to visit vehicle assembling plants across the country, you can go there and ask them what we call gig. A gig, or that is a gig is called the architectural or the structural model of a car. That before a car comes out, they have that what we call a gig. Now, therefore, a base model is that which is abstraction. In database, before you go to the physical aspect of your database, we actually have what we call a base model. That which you usually draw and actually, well, this is how the database is going. But when you implement it using a database development software, maybe MySQL or Oracle or any other software, then in that particular case, you are actually saying, oh, yeah, this now you transfer that which is space into real. So therefore, it's an representation of this property, in particular, its behavior, which is varied in all possible contexts and described. Now you can see, if I use the example of where which has given us, you take it into that abstract class, you implement it differently under different circumstances. And that's what we call possible contexts. So that also becomes what we call a model. What is its importance here? If I take you back to the various formulas that you know, and I'm going to type it, hopefully every one of us will be able to see what I'll type on the chart. We normally say there is this formula y is equals to, remember, mx plus c, right? It's a very famous formula. And we call it is a linear, this one we call it is a linear equation. But for the purpose of this class, therefore, we call it a linear model. It's a linear model. And then we call it, it's a base model. Why is it a base model? Because I can use this under different circumstances. For instance, if I'm trying to plot the performance of students, if I am trying to plot the amount of rainfall, so it's really an equation that I can apply in different situations, only that now I'll change, I define y, what's y? Maybe in terms of y, I'm maybe trying to say is a average performance. X, I maybe say it is maybe a score, individual score, you know, and then under different circumstances, I change the variables. What I will only change is what we call what does X and Y represent under that particular circumstance. That becomes what we call a base model. And therefore, when we are coming up with a good model, it must be generic, right? So the answer, the old story, therefore, leads to what we say, a model should have elements of generic. It is generic, meaning that it is adaptable, can be used in different circumstances. Now, the next thing we need to look at is what we call system as an element of a model. A system, as it were, we say is made of components which interact, right? From the basic definition, we say a system is made of components which interact to give an output, right? So that which interact in a defined manner to give an output. When you look at that, so we are saying, therefore, a model should have that ability to allow interactability of the various components in order to come up with something. For instance, the example I've given, they have y is equals to mx plus c. We want to say how do the various components of that formula interact in order to give what we want, right? So a system is a well-defined object in real world under specific conditions, only considering specific aspects of its structure and behavior. So what is important now is, if now, like the equation I've given there, I say that this equation is going to be used to model, let's say, malaria, then it means it is for that. So I will now move away from the generic, which is the base model, into being specific, meaning that now I have defined it and constrained it so that then it is no longer general. That's a system is more specific, where you have defined those components in the various angles. Now, there is another element, what we call experimental frame. Now, and in this, I'm going to explain this, but before I go into this, I want us to take ourselves into a unit you did on research methods and technical writing. Now, in this research methods and technical writing, writing, one of the things you talked about is what called population and ensemble. Now, population we say is the total coverage of an area of interest. For instance, if I want to study about student in Strathmore University, then it means my population is all students, right from diploma all the way up to PhD. Those are the students. Anybody who fulfills the condition of being a student in Strathmore. But then we move on and actually say, wait a minute, can all this be, can they all qualify if I bring in further, characteristics? Maybe I'm interested on things that touch undergraduate. And therefore, to that extent, I remove the master's, I remove the PhD, I remove also the diploma. Then I remain with the undergraduate. And then now, when I go to the undergraduate, I still now pick a representative of that. Now, when we talk about a sampling frame, is now this is very important for us to be able to understand. Remember, I started by saying the entire population of Strathmore students will have diploma, not diploma. In fact, there are those who are even doing short courses, diploma, undergraduate, master's, and PhD. But then I have realized that I do not need all this. I only need undergraduate because undergraduates are the ones who are going to answer my, question. Then now, when now I want to form a sample, then I'll say my sampling frame. That means where am I going to sample from? I will be sampling from the undergraduate. So it means, therefore, my sampling frame is the undergraduate. So we say sampling frame is that section of a population that fulfills the conditions for sampling. Now, what is therefore experimental? With that understanding, wanted to build, your knowledge from there. Now, when we come to experimental frame, we are actually saying that your experiment will be fulfilled. Experimental frame describes experimental conditions. In other words, that an environment where the conditions for you to conduct your study are met. If you look at what I described about came from the entire population of Strathmore, then I was like, no, I can remove this. I went to undergraduate because they are the ones who are fulfilling my conditions, what I call my study condition, which therefore I can actually say my experimental condition, within which a system and corresponding models will be used. And this is very important. You recognize that in this COVID situation, you hear different countries have different models to actually project on how this disease is going to affect the society. You can get it from me that a model used in Kenya cannot be used in Tanzania. Why? Because the experimental conditions are different, meaning the conditions in Tanzania and the conditions in Kenya are different. And therefore, when you are coming up with a model, you must look at experimental conditions. Now, it's important here now to mention something. Experimental conditions, we also call them assumptions. Now, you can remember many mathematical come across whereby they say assume. Now, this is important, is what we always know. Now, I want you to know also that every formula is useless without assumptions. That specific assumptions must be met for a given formula to work if conditions under which it's going to work are not met. And that's what we call experimental frame. So If it fits you, you can also call it assumptions. Then is the next thing that we need to know what we call events. What's an event? An event is an occurrence that changes the state of the system, right? An occurrence that changes the state of our system. In other words, if you change, for instance, the way something is happening, then we say it's an event. Look at what we are having, the COVID-19. Many people are saying, when the weather conditions change, like now, we are starting with the cold season. It's almost coming. Now, with the cold season coming, the conditions change. So, if therefore the occurrence of spread of this disease is dependent on such kind of conditions, then we expect therefore a change in conditions, weather conditions will maybe increase the rate of spread. As a matter of fact, if I quote one of the leading infectious disease experts in the US called Dr. Fauci, they are actually saying in their country, they are entering what they call a flu season. Now, meaning that when you have this COVID, which is a flu, and then you have another flu, so the two will actually superimpose and therefore will make the situation more severe and serious. So really an event is an occurrence which changes the state. So some of the things which influences the event is what we call conditions. And it's important now here, there is something that also we here, which comes here, what is the state of a system? State of a system, as we are going to see later on, we'll be talking about, I don't know whether you did this under artificial intelligence, what we call a Markov chain. But if you didn't do that, that's okay. I will rely on your knowledge of Form 4. In Form 4, you did something what you call transition matrix. Now, in transition matrix, you were using what you call and even Form 3, I suppose, where you are talking about translations. That if you manipulated how do you call it, a matrix, either by multiplication or by addition, you will change it into another. So therefore, the original position of a matrix can be changed by adding or by multiplying something. So meaning therefore, there was the original state, and then there is now the new state. So really, a system will always have different states. And these states are influenced by what we call an event, right? And this is so every model will always have those characteristics. So once you understand those elements and what you are calling event, then you can actually be able to do a good modeling. I think there I'm talking about that they are what we call internal and external events. Internal, we also call them endogenous, and external, we also call them exogenous. Now, for instance, if I can give another example, you know, stock markets, stock, you know, money economy, stock, like Nairobi Stock Exchange. There are things that are done, which can be done within that market, which will offset the performance of shares. For instance, there's what we call insider trading. What does that mean? Meaning that the people who are in the stock market who are privileged with specific information will try to pass that information to their what? To their people that they are representing in that market, and then they start doing what we call stock manipulation. So that we call it an internal. So that's an internal event. But then you see, like now, the performance of the stock markets in Kenya has also been a bit affected by the disease in Kenya. That can also be seen as an internal factor. But something like what you see, crude oil, like now, for those of you who are following international news, crude oil in the US are no longer selling. Why? Because the people are not going to work, and so the production far much exceeds the consumption. To the extent, some states are actually paying people to fuel, to come and actually take this oil. The reason being, the storage as farm as is now outstripped, and therefore there is that challenge. So that we call it. And how does that affect Kenya? The price of those commodities will keep on coming down in the coming days. Yes, there is a question, I think. Yes, there is a question of crude futures, that's Onyoni. Please, if you could address us, Onyoni, on this, if your mic can work, I'll give you a chance to talk about crude oil futures. Indeed, yes. I don't know what you want me to talk more about it, or you want to comment about it.
I'm not commenting anything. I was just saying it's futures.
Yes. That
Value. That's it.
Okay. Great, thanks. Actually, it's good. I'm happy. Most of you are also following that. So it's an important element to reflect on. Thank you, Onyon. What are the typical models, uses of models? So I will discuss this, and in the next, I think, 10 minutes, we'll take a short break, and we'll reconvene back. Typical uses of models is to understand the behavior of existing system. For instance, if you want to know how a stock is performing, how changes in a given an environment affect, something, you can actually use a model. You can use a model to predict effects of change or upgrade system. How does it influence the output? You may want to study new or imaginary systems, and this is quite often used. For instance, when you do not know how things are going to happen, then you can actually use models to be able to kind of hypothetically infer to how it's likely to produce them differently. I may want to use models to investigate something, and those of you may have a chance to work with investigators. Models are commonly used in investigation sciences, whereby you want to create various scenarios and try to put it. I need to be very clear on this one. I give example. In the Canadian judiciary system, they use models in court. In the US, they use what we call the jury, whereby the judge will preside and will let people, experts in particular area, to come to court and actually listen to the presentation, the argument, and then because they are experts in this, they give opinion in court. That use of the jury in the Canadian section has been automated using models. More importantly, using what we call conditional probabilities, right? So models are used in different circumstances for different situations. In Kenya, I think you saw. I think now you know what we call Cambridge Analytica. You started hearing. I don't want to go to the stories of what happened most recent past in our electoral process, but Cambridge Analytica, you can Google and read a little bit more. They use data mining techniques and the modeling to be able to create different scenarios and be able to know how things are going to play out. You've seen people who use data mining and therefore modeling techniques to be able to know to analyze their stock and their customers to predict on which stock is moving and say kind of thing. So you can use it. There are many uses of models. So that's why I've used the word typical. The other thing that I want us now to look at is what we call state variables. But before I go to state variables, I want to give you a break of 15 minutes. So we will be reconvening at 12:40. So we will be reconvening at 12:40. So we'll take a short break. I would have given you what we call breakouts, but for now, let's take 15 minutes. So we reconvene at 12:40 to continue with the remaining section. Thank you. Variables. Actually, talking about a system now, we want to look at a heuristic that it has a variable. And so when a variable changes, then we say this. So system state variables are a collection of all information defining what's happening within a system to a sufficient level. Now, for instance, if we wanted to describe the performance of a given stock, or the performance of, let's say, a business entity. So we will need various information for us to be able to describe that business. And so those aspects of variables that we need, or that piece of information that we need from that business, forms what we call variables, state variables, because without knowing, let's say, for instance, the sales per day of a business, we cannot therefore be able to say how well the business is doing. If, for instance, I wanted to say perhaps the student is going to do very well, I need to collect some data about that student for me to be able to actually say, yeah, the performance is in the right direction, something like that. The determination of a state system state variable is a function of the purpose of investigation. So meaning that what that means is that if my intention is to know the performance of the business, then I need to understand what determines performance. For instance, is it the volumes of sale? Is it the number of customers that it has it's handling? Is it the stock flow and say kind of thing? So therefore, for me to be able to know what state variables I need to know what's the purpose. So what may be the system state variable in one case may not be the same in others, and hence therefore meaning that the various variables will change depending on the circumstance. Now, therefore, ideally, state variables are characterized by the following entities and attributes. And this is very perfect because a system is whole. And therefore, what up there, you remember we talked about an entity, we looked at an object, and we said an object would have, attributes. And therefore, a system is made of entities. And so entities, they have attributes. So, and those entity objects, we can actually explain them in terms of their what? their characteristics. So an entity represents an object that requires explicit definition, which I think we discussed it a little bit. And then the other one, an entity can be dynamic in that it moves or it changes. You know the word, and that's why I put the word moves in quotes, meaning it can change. It doesn't have to be, the same, or it can be. It all depends on how you declare these things. So an entity may have dynamic attributes and static attributes. For instance, this afternoon I'm chairing a meeting, but I think it has been, I don't know whether it has been called off, but I'll check. But initially, I was scheduled to chair a meeting whereby we are looking at coming up with a dynamic database. So if we are going to come up with a dynamic database, it means this data we are going to store in that database is dependent on specific triggers, right? So that now I am not always saying that in the what is stored in the database is or what the defines a given data element is this, but we are looking at what will influence the properties of that particular attribute. So there is what we call dynamic objects, meaning those whose attributes keep changing, all characteristics keep changing, and there are those which are static. For instance, in a customer service system, a bank customer is a dynamic entity, whereas a bank teller is a static entity. How does it make? How does it work? You see, when you go to the bank, the teller will always be there serving, and will serve many customers who are coming. So meaning, therefore, when you are going to design such a system, it means the attribute of a customer, the entity called customer, has to be dynamic. The entity called bank teller would be maybe static in that, but it will reflect on this. Or even better, in the supermarket or in the stores, you realize that the teller will be there, but these are the customers keep changing. The customer will be different. An entity may have attribute that partition to that entity alone. That attribute should be considered as a local value. An example of a customer in a bank, an attribute of the entity customer could be the time of arrival. So meaning that the time of arrival for customer 1 is different from the time of arrival of customer 2, because they are going to be different. In that particular case, therefore, we say time of arrival is a local. And therefore, you see, when you go into the design and the modeling of this, you see that attribute has to be a local value, and therefore you can declare it as a local variable. A state variable. A resource is an entity that provides service. A resource is an entity that provides dynamic service to a dynamic. Now, that is, for instance, the resource can serve one or more than one dynamic entity at the same time. So in the next one is operates as a parallel server. An example here is this. For example, idle, busy, failed, blocked, or starved. In that case, what does it mean? It means this. The teller, not the teller, the customer who's coming, there is a time that this person is being served, and there is a state when this person is not being served. Okay, so in that particular case, this person, when he is waiting in the queue, is consuming a particular resource, and the resource could be in the form of because this person is standing there idle, is consuming, we can actually say is consuming some space. And that space is as a consequence of the state they have found themselves. And what's that state? That state is of idleness. So we normally say there are many possible states of the resource, right? So this resource that we are calling a customer, in that particular case, is at an idle state. Maybe busy and say kind of things. Dynamic entity can request one or more units of a resource, meaning therefore the dynamic, the teller can actually invite, and you have actually seen, I think, cooperative bank, I think I've implemented this, where they actually tell people sit, and then you see the counter calling. So when you are not called, you are in an idle state. When you are called, it means the dynamic, resource is calling for, is going to a particular element to be served. So if you reflect on those, it becomes a little bit clear. There's the listing process. Entities are managed by allocating them to processes that provide service by attaching them to event notices. What that means here is like when you want to come up with a system, you must actually almost determine how the processes are going to go. And these processes, we say in other words, how events are going to be sequenced. How events are going to be sequenced. For you to reflect a little bit more on this, is you are looking at how a computer performs its work. We normally say it can perform its work through scheduled events. And some of these scheduled events will follow. There are two fundamental ways of processing. There's what we call first in, first out, or last in, first out, LIVO or VIVO. So depending on that, so it's possible that a system may be configured to use first in, first out, or last in, last out analogy. Other aspects of the state is what we call activities and the delays. An activity duration of time, when duration is known prior to commencement of the activity. Thus, when the duration begins, it ends, can be scheduled. So what an activity in the context of system modeling is that which we can allocate time. Let me just put it that way. Is that which we can allocate time associated with time. Like we can actually say K has start time T1 and end time T2. So in that particular case, then that is an activity. Anything which is associated with time, and that's what we call an activity by definition. And that is very important. That basic definition I've given is very important in modeling. You are going to see what we call stochastic processes. This is important. That let's have it now in our thinking that an activity is that which is going to consume time. Now, of course, also an activity can consume a resource. Okay, can consume other resource like computer memory. But for the purpose of modeling, that is not what we want to deal with. What we want to deal with is that which consumes what? That which consumes time, or which we can associate time. And that's very important. And therefore, we can basically therefore see a constant activity, meaning that which does not. I mean, the time is always constant. There is that which is going to be variant activity. That means time is going to change. Now, when I say time is constant, it means every now and the time that it only requires maybe 10 seconds, 10 seconds, 10 seconds. That means that's constant. Variant time is when in one instant it takes 10, another instant it takes 16, another instant it takes 9, another instance. In that case, you are talking about variant activities. Okay, that's why we say duration can be a constant, a random value from a statistical distribution, the result of an equation input from a file or computed based on the event. So what it means, and say that we understand each other here, if you reflect on algorithm analysis, you talk about constant algorithms. Now, a constant algorithm had what we call constant time, meaning that we can, in other words, the time is always the same. Now, variant activities is that which is going to be stochastic in nature. Now, when I talk about stochastic in nature, meaning that is probabilistic, random, like the one I've given, one time 10, another time 16, another time 9. So you can see it is quite distributional, statistical distribution, meaning that we can't get to know where the next one is unless you know aspect. Now, a delay is an indefinite duration that is caused by some combination of a system. So meaning, therefore, it's possible, and you can also have a system is occasioned by what we call a delay. Meaning, in this case, we are saying you do not know when that is going to end. A delay is indefinite duration. That means we can't actually for sure say it is 20 seconds, it's 1 hour, it's indefinite, and that's what we call a delay. So obviously also a delay is occasioned by what we call a process. This is important. So remember, small activities add together into what we call a process. And therefore, if there is a delay in one activity, it leads to a wholly delayed process. Having looked at what we call the state variables, I need to give a recap. State variables, we are actually saying that it's characterized that for you to define a state variable, because in other words, a system state variable are all attributes of a system. For instance, the example here that we are using, for instance, is a bank system or customer serving system, where in this customer serving system, we want to look at a customer as an entity, a teller, if it's in a bank, or how do you call them, a store, or a supermarket. It is that's also an entity. So when you look at these entities, we can associate them something. We can see they can be both static or they can also be dynamic. And we are actually saying that being dynamic, meaning that there is the element of change. And this change that you are saying is change of state. And there can be no change of state. And this is non-change of state, we call it static. An example, therefore, at one point, the teller will be there to serve. But a customer at one point is doing, is in an idle state, seated, waiting to be served. At another point, he or she is being served. In that particular case, we say they are very dynamic. We've also said that there are attributes that will influence an entity, and these attributes, we can actually call them or refer them into internal, and also we can also look at external. We are saying that state variables will have resources associated with them, and these resources, therefore, are those which we can actually say are to be consumed, and we can relate them to that which, therefore, when they change from a given state, they assume a given resource. The processes involved in a system, we are saying we can list them on this. Fundamentally, there are two, vivo or vivo, but commonly vivo is the common one, that is first in, first out. For most systems, they use vivo mechanism, that because in that particular case, I'm trying to prepare you into what we call queuing system. We have also looked at activities and the delays. And the activity I've said in this particular case is anything that we can associate with time, that it has both the start point and the end time. The reality on this is that I'm preparing into what we call stochastic process. Now, then the last discussion point here is what we call classification of models. Now, models are like classified broadly. Now, not so classified in a broad sense into two. But of course, there are many others, but broadly into two. But there are others, as you can see. The broad definition is what we call probabilistic or stochastic. So when you hear somebody saying this is a probabilistic, is the same as saying a stochastic. What does it mean? These are those models which takes variables that are random. In other words, they use the concept of probability. For example, the one I talked about, that a customer is coming. We can actually look at customers coming to a supermarket. You see, you cannot know in 2 hours time how many customers are coming, or in 10 hours time how many are coming. What you know is that they are going to come, but you don't know how they are going to come. That element of not knowing how many are going to come, it's dependent on chance. Their arrival is really dependent on chance. They come at random. Okay, nobody calls the other that let's meet in the supermarket. So that we call it a random behavior. So stochastic or probabilistic occurrence are those that we do not know the chance of occurrence. The chance of occurrence is by purely chance. Deterministic is that which we can almost tell for sure that this is going to occur. You have some element of certainty. You are sure this is going to happen. An example there I'm giving: position of a falling object in a vacuum. If you know, I think since you guys you can remember your physics, a pendulum. You see, with a pendulum, if you use the example of a pendulum, you know, once it is displaced, you can almost tell the position, that displacement of the pendulum, which position it will take after a given time interval, because there is a formula you can actually use, right? Or if you are having an object falling, and you know the law of gravity, which is a formula also, you would actually be able to know, given the weight of this object, and therefore at particular time, this object will have fallen up to here. So that one, we call it deterministic. We can determine it using a given what? A given formula. We call it deterministic, and they are not random in nature. So when you look at all these models, so why are we looking at this? This is a very important part of your study. Is like in an environment, you want to look at a system and actually say, well, this is a deterministic process, or well, this is a probabilistic system. Without first of all classifying that way, then there's no modeling you will do. In other words, you want to ask yourself, what this system that I'm seeing, is it deterministic? In other words, can I actually say this is what it's going to be with surety? If that is it, then that is deterministic. If you can't say with surety, it is by chance, then that's probabilistic. The understanding then of this will then assist you to get know the modeling techniques that you take, you apply. So those are those which are based on behavior. And in most cases, you'll find them, they fall under this. In fact, the ones that we are now bringing in, they fit into behavior-based system modeling. There are also models which are classified based on events. Okay, and it's important that we understand each other here, that we can have an event which is time varying, which is probabilistic. And I'm going to give examples shortly. And we can have an event which is time varying, which is deterministic. So that's why I said that the beginning is on these two. If you understand these two, then the rest will fit into them. And I will allow time for us to reflect, and even I will be glad to take questions from your side. Now, there are those which are classified based on time varying. Time varying, there are two, what we call discrete time model and a continuous time model. Discrete time model and continuous time model. Now, discrete time model, these are systems that system state change at distinct time. System state changes at distinct time. What does it mean? It means, I'll give an example. I think I like this example I'm giving you. I've used it in particularly when I was modeling student behavior. Not really that I'm interested to really predict the student behavior, but I was using it in a unit called probability modeling. This is way back as in another university. What does it mean like this? You know, at one point, we'll have student in the hostel. At another point, we'll have student in class. At another point, we'll have student in the cafeteria. At another point, you will have a student in none of these three places. So what does that mean? It means the state of the student, be it he is in class, there is no way that that student will be in class at the same time he's in what? He's in the hostel. Their state is dependent on the time. You can see in that particular case, is also dependent on the resource that we looked up there. So in that particular case, these are the distinct time, different time. So distinct time here means we can say at time T1, and this one, I think I will put this one because now we need to start talking about T naught. We say hostel, okay? Then we say T1 as class, okay? Then T2 maybe cafeteria. Okay, so you can see, so distinct time is distinct. T1 is the initial time, T2 and it's maybe final time. So you can see what is happening with the student is dependent on time. In that case, we call it distinct time. And therefore that becomes a discrete model. So there are things that we can actually model in that particular manner. And we can also say it can be defined as one in which the state variable change only at those discrete points in time at which events occur. Number two, as I said, the other one which is based on event, rather based on time, is what we call continuous time model. Continuous time model means allows a system state to change any time, right? Allows state to change any time. What does that mean? It means if it is like this, in the way we reflect on this, it's like saying T naught, like we can say in that case, the state of T naught is equal, it's more or less like equal to T1, something like that. or you can actually say T2 is equals to T naught. In that particular case, you see, it is the change is not dependent on this distinct time. It is dependent on something else. All right. So in a continuous time model, state variable change continuously as a function of time and are generally analytical method. That's why I'm saying on something else. But on the first one, we are saying distinct time. So the discrete time model is distinct time. But on continuous, we are saying it is time and more or less something else. So time is invariant. So times is generally continuous. That's why I call like deductive mathematical reasoning is used to define and solve systems. So those are some of the models that are classified based on time. There are those which are also classified based on system state itself. Now, those which are classified based on state itself, we talk about static model, and I think we have talked about them up there, and dynamic models. Now, static system description at one point in time does not consider time. With it, it is time is not what you use in modeling. So with it is that it's more of attributes. Is more like of what we call the behavior of the system, but not time. Then dynamic is also system description as it changes in time. So the converse of dynamic model and static is that static is not going to depend on time, basically so much, but it is a model. It is at one point in time, not, it cannot, the state of it does not necessarily change. For instance, if we are having, let's say, time T1, in other words, it's like this, saying T naught is equals to T1 is equals to T2, which is equals to what's there. So that is a perfect illustration of a static model, meaning the event has not changed. The state has not changed. Now, but dynamic is like this. It's like we'll say T naught is less than T1, and is less than, which we can say is less than T2, and therefore we can actually say is not going to be equal to, because I can't get that not equal to, allow me to actually use another way in which is not equal to hostel or class or cafeteria. Cafeteria, like that. So what do I mean here? It means as time changes, the state changes. That's what dynamic means. System description as it changes in time. Dynamic model changes with time. And that's why I'm saying T1 is T naught is smaller than T1, and therefore is not equal to being in hostel, nor is it equal to class. It's all depend on a number of things. But there is an example here of other systems that you can actually look at. Examples of different systems: queue length at a cash machine. The queue length at a cash machine, this is the ATM, can be stochastic. Remember, we said stochastic is that probabilistic. You do not know whose which queue position you will be and who will in the queue. Therefore, it is a stochastic thing, probabilistic. Discrete in the sense that you can actually be able to tell maybe in 8 a.m. it is there were 2 people. 10 p.m. there were 10 people. So you see, we can actually be able, that is discrete. And therefore it is discrete time and it's also a discrete system. Motion of planet, we call it deterministic. We know the formulas that are used to get to know how to determine the position of the planetary motion. So you can actually determine that. It can also be continuous because the change, and as I've actually shown there, it is at one point, if I'm looking at the planet Earth, we know when it is like right now, we know it is in a particular position. Later on, it's going to be in a particular position, changing continuously. And it can almost be seen to be time differing. There is a question here. Musia is asking whether the nodes are on the e-learning. I think so. The nodes are there. Hildegard Musia, I think they are there. Maybe you missed the first lecture. I think they are there. You don't have the enrollment key. Then you can get it from the module leaders. And among other examples that you can look at that. So there are these questions that are here to have a reflection. Is there a difference between discrete system? The answer is no. It is the same, because the discrete time, and you can actually see from where notes up here. We said time varying model. That's where we have discrete model. We say changes on that. So when you finish with that one, so you a discrete system. So what you are actually having, here is we are saying, and this will okay. Now I where you are coming from. I remember when I started my explanation here. To give a recap, is that really models are classified into 2. Probabilistic and deterministic. And then I went on, I said that you can have a discrete time model being probabilistic. And I also said you can have time model being deterministic. I think I mentioned that. And then, so what we are actually having here is indication that okay, is like a classification, is a day scorer. That scorer. If we can actually look at that. And then this is a student who's a day scorer. We can actually say self-sponsored. All right, something like that. So you see, we can have we can categorize. So you can see we are trying to look at how we categorize this student. We are categorizing this student as a scorer. So meaning that we are using a residency as a basic. Maybe I think I need to do this in the chat, then we can actually be able to see it better. You see, I am looking at a student classified based on residency. Okay, so in residence, we can say the scorer. There is a scorer as an example, and then I can also say classified. Classified. Based on sponsorship. Okay, then here I'll say self sponsored. Okay, so meaning that I am having two categories of classification. So you see, if I am now coming up with down there, I'll actually say I have a student. So a student, I will say the scorer, self sponsored. Okay, something like that. And then generally, therefore, when I something like that. So you see, meaning I am combining those. So what does it mean? It means a student, or I can also have a student again who's now day scholar, now sponsored, right? Sponsored. You see, at that particular case, what are we seeing? We are saying sponsorship is a subset of, the based on residence, something like that. So that is basically what I'm trying to come up with down there. So in essence, I'm saying you can have a model which is discrete but probabilistic, discrete but deterministic. So the starting point always is here. And that's why I said always get to see what your system is probabilistic or deterministic. All these other things are inherent elements which determine where you can put. So when you come down here, so we are saying there is if a stock, we have a system Q, this that we are calling a Q length at a cache machine. So we are saying it has element of deterministic, not deterministic, but probabilistic, and therefore it's stochastic. And then it is, it's time, it's discrete. It can't be continuous, it's discrete. So generally, therefore, that system that you are going to come up with is what we call discrete system. Okay, a Q length, but it can't be a Q length for this matter. Something else. If here it's continuous, and as you can see somewhere here, but the deterministic, you see, it is a discrete system. That's the motion of our planet, because we can determine some time going on, so we can model it at the end as a what, as a no, this one here is wrong. This one is here. Please, this one I can edit. This one here I write. Hopefully you can yes, that one that I put in yellow, change. This is discrete. In your notes, when you get this, is discrete, not discrete, continuous, because it is continuous. What determines a system whether it's continuous system or discrete system is the time element. So if here, like now here is discrete time, therefore the system is time, rather discrete time. If here it's continuous, then it's discrete system was question that came from Jaden. Thank you for that clarification. So there are questions down here for you to reflect on that you can download and actually reflect, and that gives you a good exercise. So I want I want 10 minutes, not more than that, to answer this one. I need to give you a simple question. These two. Give a sample of each stochastic model and continuous. And X models. It will automatically put you into breakout. So you check your breakout. So so you can check you are 4 each. Okay, so you are 4 each in each of the rooms, and there are 26 rooms. You've been assigned, so you check on your breakout rooms, meaning those are your groups. So try to answer those questions in 15 minutes. We will convene. I will be asking you the first person in each group. For instance, breakout room room 13, Onyoni is the chair. So if you are in the first, when we one the group found. So take 15 minutes to answer that. We'll reconvene after 15 minutes. So you check through, you see which room you are. You click on the room, and then you'll be able to know which room you are. There are 26 rooms. Everyone has been grouped. What and there are those who are saying been assigned. So the answer is everyone has been assigned a group. Check it from, so I'm posting for those who don't have the, please check on the breakout schedule. I remember we said for purpose of clarity, you don't actually, somebody is trying to do something, you risk being locked out of this platform and hence removed from these classes. So please use other means to communicate. So I've actually said under the more menu, if you go to your pattern, there is a section called more menu. In the more menu, there is the chart. Then what follows below it, there is breakout rooms. And in the breakout rooms, I can actually show you what I have. Group chairs, any group can start, and I want to believe you first you to start by explaining your take. How was the discussion in the breakout room? How did you find it? And then you give your group feedback. So we can start with any group. So you raise your arm, and then I'll then be able to give you a chance. So let's start with any group member, the chair. You can raise your arm, and then I'll be able to give you a chance. Okay, and then I can go this way. Let's start with a group where Nicholas Mimba was. Nicholas Mimba, who was your chair?
Oh, sorry. Yes, our chair was Sam Mulwa.
Oh, Sam Mulwa, yes. Sam Mulwa, you can present all, Nicholas, you can present on the behalf of the group.
Hold on. Let me talk to Sam because he has the points. We'll get back to you shortly.
Oh, great, great. Oh, Sam is up now. Yes, Sam, go ahead. Yes.
Okay, the group discussion was okay. The group members participated well. Thanks to Roseanne, she gave very nice points.
We can grab for her. Do you know how to grab for her through the platform? Maybe I'll show you next time. But thanks, that's good. Yes.
So our examples on stochastic were given by Miriam, I think. She said that there was queuing models, investment models, and financial models. Then the continuous models were given by Mangak. He said the amount of water flowing into a dam, the traffic models, pedestrian models, and inventory models. So we came up with those examples and we all agreed.
Oh, great, great, thanks. The other random generation of the groups, you guys will be maintained that way, because in fact, one of the examples I'm going to use in, I think, our third lecture, is it third or fourth? Should be fourth. I think it should be fourth. The fourth lecture is the water flow, the tank model. So I'm very happy you were able to identify that. Thank you, and I wish you well. We'll be able to discuss that. And I think I'm happy with the examples that you identified on the stochastic and the continuous. One of the stochastic model, I have actually modeled it. I think towards the end of the course, I'll show you how I have actually applied these things in practical sense. Thank you. So we can then go, that group has done well. Let's go to a group Walter Nyaganga. Was Walter, you were in you were the chair or who was your chair?
I was the chair.
Oh, great.
We were in the group with Kevin, Gogi, and Brian.
Yes.
So for the stochastic models,
Yes.
we had two: supermarket model
Yes.
and hospital model.
Yes.
For the continuous model, we had again two:
Yes.
a model for weather changes
Yes.
and a model for stock market changes.
Okay. Oh, great. How did you, maybe if I could, how did you find your breakout sessions?
The breakout session was good. Everybody was contributing,
Yes.
and everybody had the chance to give their views on the different models.
Oh, great. Great. Thank you. Thank you. We'll be able to interrogate more about those. For instance, the stock market model that you have mentioned, we'll try to manipulate and interrogate further those. Thank you. Thank you. James Boro. James Boro. James Boro. Yes. Yes. How are you?
Fine.
Yeah. You were the chair.
Yeah. Let me just speak from David.
Oh, okay. Okay, great. Seems Peter Onyango wants to talk. Unless, yes, Boro is here. Yes.
Okay, he can talk first, then I'll go after him.
Oh, okay, okay.
Okay. Can you hear me?
Yes, yes, Victor.
Oh, okay. So for stochastic models,
Yes.
we found one financial service, one model called Monte Carlo simulation.
Yes.
It's a simulation for financial services, and there's for continuous models also found. We centered on a commercial flight simulator.
Okay.
Yes.
Oh, great. Thanks. I hope again you'll continue refining that. How was the discussion in your group?
It was okay. Everything went well. We all contributed to the group
Oh,
discussion.
great.
Yes.
Thank you.
Excuse me, sir,
Yes.
but I'd still want if you could explain continuous model further. I really didn't understand it.
Okay. Yes. I would actually explain. Allow me to explain once I receive the comments from a few groups at the end.
Okay.
I hope that will be good, James.
Okay.
That be fine
Yes.
with you? Oh, great. Let's see, Alan Bikuru. You were in which group? Was the chair? If you were the chair, you can send.
Sorry, hello.
Yes, hello, how are you?
I'm fine, thank you. How are you?
Fine, thank you.
So in my group, we weren't sure who was the chair, but we all participated. So
Yes.
we came up with two major points.
Mm.
An example of a stochastic model would be a chess game,
Yes.
and that of a continuous model would be the foreign exchange system.
Okay.
Yeah.
Oh, great. Oh, that's nice. Let's hear from Emmanuel Okwiri.
Yes, so in my group,
Yes.
for the stochastic model, we came up with a financial system,
Yes.
a project management system, games of chance, such as
Yes.
chess,
Yes.
the stock exchange,
Yes.
and weather prediction system.
Okay.
For the continuous, we had a census population system
Mm-hmm.
and a water flow system,
Yes.
and a model to predict the COVID data.
Okay.
Yes.
Oh, great. We'll try to interrogate them further in the coming days. Vanessa has a question to ask. Yes, Vanessa.
It's not really a question.
Yes.
I was in Emmanuel's group. I just like to add, under the continuous system, we
Yes.
also had the BMI.
The PMI system.
Yeah, how to use people's age and weight to determine something.
Oh, okay, okay. Yeah, and thank you, Vanessa. In fact, I will a student who did some work in last year. She didn't complete. I think there were some areas that she didn't finish, which I feel could be enhanced to make it really work. She was tackling things to do with using those what you have talked about. We call them biomarkers. Those biomarkers to be able to determine the likelihood of somebody becoming rather falling sick, or how do you encourage this person to reverse some conditions. So whoever came up with that one, I can't remember the name of the lady, but it's something that we can check on, and I'll be glad to be of help, whoever who came up. Then there must have been a thought process that went through it, and it's a good study, research. Thank you, Vanessa. Now, because of time, I may not get from everybody, but I want to appreciate a discussion that you had. And I encourage you to continue the discussion, to not just end here. Learning is something that we can always carry on and actually try to understand. But allow me to then explain a question that was asked James Boro, that perhaps what is really this continuous system or continuous model? What we have put there, we say models allow system state to change anytime. So unlike the discrete time, in the discrete time, the changes will occur at a specific time. For instance, you see, if let's reflect on what we say, systems like weather. If you are dealing a system which is using sensors, and then a sensor will correct. For instance, if you are looking at climatological issues, like now what's happening in Kenya, and if I'm a farmer, I want to know the humidity level, so that then I can maybe open my tent, and not how to call them, those tents, they call them the greenhouse. So, and in fact, on that, I would want anybody who's interested in an IoT. There's something I wanted to supervise the people on that one. You can always we can always chat. But let me explain this one. You're looking at in the greenhouse, there's the use of sensors, and now these sensors, you see the humidity. A change of humidity is something which is at any given time you can measure humidity. You don't measure humidity in the morning. That humidity can only be measured in the morning and measured in the afternoon and in the evening. You see, when you deploy a sensor, you are able, the recording of sensor, you can record humidity at time 0, 0.1, like that. So in a manner that it is not that it must be at let's say 8 a.m., 10 a.m., 11, but it is something which is occurring generally. That if I want to capture humidity, I can capture it anytime. There's somebody who's messing the screen, please. So then what that means, therefore, that element of change of state anytime, meaning that the humidity recorded by the sensor anytime in the greenhouse is not going to depend on time, but it is occurring in a continuous manner. So that's what we call a continuous model, continuous time model, meaning that anytime I wish to correct data, I can get it, but it's because that and the sensor, basically the sensor, when you plot the graph of humidity, it will be something which is continuous. It will not be points, but a continuous, thing, because you can have humidity at time 0, at time 0.1, 0.2, 0. So it's really continuous. That is what it is. In a continuous time model, the state variable change continuous as a function of time, and generally analytical method like deductive mathematical reasoning is used to define and solve the system. Never mind on the aspect of solving. I am not sure whether that aspect, there are two ways of solving mathematical questions. There is what we call deductive and inductive. So I wouldn't want to go to that aspect. There will come a time I'll talk about those ones. But what's important is to get the analogy here is like, which are those circumstances where a state variable, and in this case, like now I picked, if I'm looking at greenhouse management system, I'm saying humidity is a state variable, is a variable that explains the conditions that are occurring in the greenhouse. So you can see humidity is going to keep on changing, which you can also say even temperature. The temperature you record, you can decide to take it continuously, and therefore you report it as a continuous graph. I don't know whether that gives some clarity, James. James Poro, does it bring it a little bit clearer, some clarity to it?
Yes, it's clear now. Thank you.
Most welcome. Now, we have a comment also. I think there is a comment. I don't know that. What is the difference between probabilistic and a continuous time model if both the state can change at any time? I remember to have said, Anton, thank you for your question, that essentially probabilistic, which we also call stochastic, and the other one which we talked about, deterministic, I think perhaps I'm going to allow me to draw a diagrammatic learning for you to be able to see. It's like if you remember the classification which some of you did in biology, most of you did biology in Form 1. You see, there is what you talk about, the first level of classification, the apex. So the apex up there, we are saying we will start with the foundation of classification of model is that broadly they are classified into probabilistic and deterministic. Under probabilistic, you can have continuous and discrete. The same under deterministic, you can have continuous and discrete. Further still, you can have a time which is discrete, which is static, and which is dynamic. So allow me to put that into a graphical way. In that case, then it will assist you. But if it can be sufficient for now, we say continuous is a subset, can be a subset or a form of probabilistic, meaning that there is a probabilistic model which is what continuous. I'll give you a simple illustration. If you remember normal distribution, the normal distribution. I don't know. Normal distribution, probability distribution. If you remember the normal probability distribution, the normal probability distribution is a continuous function, and it is when we say it's a normal continuous, that is a continuous model, then we normally say it is probabilistic because it's dependent on probability, right? In fact, we are going to tackle, it's one of those that we are going to tackle. I've not posted the materials there. Now, when you go into a binomial, okay, binomial is not continuous, it is a discrete, all right? So those are the examples. I didn't want to go to the mathematics because then when I start on this, then somehow I will be jumping. We'll be tackling this in, I think, chapter 4. In fact, chapter 5. So those are the examples. You remember the binomial that you did in high school and also you did in your probability and statistics class. And the normal distribution which you did. Normal distribution is a continuous function. It's a continuous function which therefore is probabilistic in nature. Number 2, binomial is a discrete function which is probabilistic, because in binomial you also have in binomial you have you can find what we call probability distribution function of a binomial, which is expressed in terms of probability. These are the probabilistic functions, but you can see one is the first one, normal, is continuous. The second is discrete, but they all belong to what? They all belong to what we are calling probabilistic. I hope that, Anton, clarifies a little bit. Anton, have I tried to make it clear? Most welcome. So we are past 2 minutes. My apology for those who attempt to end. We will stop at that particular point. We will convene next week. But before then, I'll have drawn the diagram that I've indicated to bring it a little bit clearer. Otherwise, I want to wish you well, keep safe, and continue discussing, and let's see how it goes. Oh, there's a hand by Musia. Yes, Musia, yes, please ask. Hildegard, my apology, Musia. I saw your hand up and it has gone down.
Sorry, it was a mistake.
Oh, most sorry. All the best. I want to wish you all the best, and therefore we can stop there. Our class is ended. We wish you well.